So, I'm going to attempt a 1957 Math A-level paper today. I did my A-levels back in 2016. I graduated with mathematics from university, so this should be easy for me. But as we all know, back in the day, exams used to be tougher, so I decided to test it, and you'll see how I fail. Right, so let's dive in to the first question. Solve for x and y the equations 2 to the x, 3 to the y equals 5. Okay, so let me write it down. Giving you answers correct to 3 significant figures. Alright, so we should be expecting a non-integer answer in this problem. Let's try and apply a natural logarithm to both of these equations. So we will get ln of this product equals ln 5, and the same will happen to the bottom line. We get this. Right, so now we can simply use the rules of logarithms, so we can split this product inside logarithm into addition of logs, and then we can bring the powers down. So we will basically get x ln 2 plus y ln 3 equals ln 5, and down there we will get x ln 4 equals ln 7 plus y ln 9. It's a system of simultaneous linear equations, and, well, we can do it. So let's not waste time. It's just the first problem. In the real exam, I would complete it. Now the second question. By putting a equals minus b plus c, prove that ABC is a factor of a cubed plus b cubed plus c cubed minus 3abc. Alright, so I think what they're trying to say is that if we plug in this value, if we plug in minus b plus c instead of a, we should get 0, right? So let's try it. We will get minus b plus c cubed plus b cubed plus c cubed minus 3abc. So here I also replace with a minus b plus c, so I'll get plus 3b plus c times bc. So now if we expand it, by the way, here's a nice exam trick. If you ever forget how you expand those brackets, you basically draw a Pascal's triangle like this, and then this is the third.
5 years later.
Why do they always ring when I'm making a video? Anyway, let's go on with this. So we look at the Pascal's triangle, and the corresponding row tells us the coefficients in front of the terms. So we will get b cubed plus 3b squared c plus 3bc squared plus c cubed plus b cubed plus c cubed, and then plus 3, it's going to be b squared plus b squared c, plus bc squared. Alright, so we can already notice that a lot of things will cancel out. So b cubed will cancel with minus b cubed. Yeah, it's here. This guys will cancel, and also these guys, because they're negative. Wow. So it is indeed a 0. So instead of doing long polynomial division, we simply plug it in and get 0. Now they also want us to deduce the factor of this guy, minus z cubed plus 6xyz. Right, so what kind of relation does it have to the initial polynomial? If we use 2a instead of a in the first polynomial, we will get exactly this. Not exactly, because we also need to change c to minus c, right? So a needs to go to 2a, and then c needs to go to minus c. And we get exactly this polynomial. And that means that a plus b plus c turns into 2a plus b minus c. So this will be the factor. Whew. Wow, so that's just first question done. I already feel like I'm at the end of C1 or C2 paper. So this is some heavy algebra in the beginning. It's not a very easy start to an exam, at least for a person of my generation. Right, so let's move on to question 2. Show that if a is more than 0, the function has a least value infinite. Okay, so this is a pretty easy question, and the students who do A-levels will know about derivatives. So this one is easy. You just differentiate and find a point where it's 0. So let's not waste too much time on it. Find the values of a, b, and c if the function has a minimum value. Okay, so this is basically reconstructing coefficients given this minimal value. So again, you find the derivative, you will be able to form an equation in terms of a and b, blah, blah, blah. All right, so this is something we can do. It is expected from core level mathematics, so let's move on. Question 3. Find the values of a and n if the first 3 terms of the binomial. Okay, so this is actually also quite standard in modern exams. So it's a binomial expansion. You should basically remember the formula with factorials and Cn choose k. So this is pretty standard. The second question, find the expansion in ascending powers of x as far as the term in x squared. Okay, so this is about combination of binomial expansions. So 3 plus x. So 3 plus x on top, and then we multiply it. So we should rewrite it like that. It's going to be 4 minus x squared plus, and then we also write this as a power, so we'll get 8 minus 2x squared to power 1/3, all to the power minus 1. So it's like so it looks like a double application of the binomial formula. And again, this is something you may expect to see, maybe not that difficult, but something similar can be an exam. So again, let's skip it, because today I was really concerned about the difference between exams back then and now. So let's look at question 4. Prove that unless x equals 1, the sum of the series is that. Okay, so I think this is also quite a standard result for C2, but it still has a very nice proof, so it never hurts to recall it. The sum of the series is that. Okay, so I think what happens is we have this sum. So first of all, it's finite. Okay, that's important. Otherwise, if it was infinite, it would only converge and have a closed form formula. only if x was less than 1 in modulus. And I think the trick here is to multiply both sides by x. So we shift the sum by x, and the last term becomes x to the n. Now the trick is to realize that when we subtract the second line from the first line, so we subtract it, we basically get s times x minus 1 on the left side, and then the right hand side will have minus 1 plus x to the nth. And so the sum becomes x to the n minus 1 over x minus 1, which is the same as 1 minus x to the nth over 1 minus x, which is how they want it. So, part 2. By multiplying the series by 1 minus x and summing the resulting series, find the sum of the series S prime. Right, so this is slightly complicated, but they give us a hint. So S prime is 2 to the x plus 3x squared plus, and so on, plus nx to the nth minus 1. Now they tell us to multiply it by 1 minus x. So we will see something like this happening. Okay, so that seems quite strange. And then the last term will be this. So they want us to produce a formula for this guy. And okay, if we expand the brackets, we will get 1 minus x plus 2x minus 2x squared plus 3x squared minus 3x plus n x to the nth minus 1 minus nx to the nth. So, okay, some terms will combine, and I guess there is a pattern. So it's almost a telescoping sum, and I think the outcome will be 1 plus x squared. All right, hey, so it looks exactly like the first series in the first question. And then, so we will see x to the nth minus 1, and then the last term will not have anything to combine with. Right, so if you remember the first part of this question, we can understand that it becomes 1 minus x to the nth over 1 minus x, but then we also subtract this guy, so that seems correct. And now we understand that S prime, our initial sum, is basically this expression divided by 1 minus x. So it should look something like this. I haven't tried these problems before. I may be making a mistake, so take some time and check my answers if you fancy it. Alright, the third question. Consider what happens to the sum of each of the given series as n. Alright, so this is a very nice question, which is asking a student to consider a limiting behavior of these sums. And of course, if we assume that x is between 0 and 1, then these sums will not go into infinity. But as n goes to infinity in the first sum, this guy will tend to 0, right? Any number between 0 and 1, if we multiply it by itself, it only becomes smaller and smaller. So the formula will become this. And here, a similar thing will happen. So actually, does it mean that this term disappears? So basically we will have 1 over 1 minus x squared. Right, so that's interesting. When n is big, these two sums are almost the same. We just divide by 1 extra 1 minus x. All right, so I wouldn't expect this type of question at a modern A level, because this is more of a university type question, you know, limits and everything. But still, it's quite thought-provoking, so I like it. Now, let's go on to the next question. Prove graphically or otherwise that the equation has only one root and that it lies between 3 and 4. All right, so they have factored it, so it should be helpful to us. X times x squared plus 20 equals 100. Okay, so I like graphic methods more, so let's try and understand what it looks like on a graph. All right, so this guy will always be positive, strictly positive, because x squared is at least 0. And because this number is also positive, that means that we only exist in the positive x realm. So when x is negative, our curve does not exist. Right, so why do they tell us about 3 and 4? If we bring everything to the same side, minus 100 equals 0, let's try to plug in 3. We will have 3 times 29 minus 100, and this will be less than 0. But if we plug in 4, we will see that it's 4 times 36 minus 100, so it's more than 0, right? So somewhere between 3 and 4, our graph crosses the x-axis. Now, how do we understand that there are no other roots? Well, I think that for x less than 3, this product, x cubed plus 20x, will always be less than 100, right? That seems plausible. So basically, once we go past 3 in the left direction, we will always stay negative. And then if we go beyond 4, we'll always be more than 100. So x cubed plus 20 will be more than 100, and it will fly off to infinity in the positive direction. So the graph looks something like this, I suspect. It's a cubic. And like we said, it shouldn't exist anywhere in the first, second, third quadrant. So maybe the y-axis is the asymptote. It was a while since I did all these problems, so I might be confusing my understanding. So I might be confusing a lot of things here, but I guess my reasoning is kind of clear. Question 6, prove that tan... Okay, this is a trig identity. So tan theta, I will start expanding straight away. So on top, we will have this. And if we should remember that cos 2 theta is cos squared theta minus sine squared theta. And of course, 1 minus sine squared theta gives us another cos squared. So this fraction becomes 2 sine theta cos theta 2 cos squared theta. 2's cross out, and then 1 cosine goes away. Okay, yes, so it is definitely a tangent. And hence obtain tan 15 degrees. Okay, so the way I would do it would be to say that, yeah, just basically apply that formula. So we'll have sine 30 over 1 plus cos squared 30. Sine 30 is famous. It's 1/2. And then cos 30 is, if we have a triangle, so this is 1, this is 2, this becomes root 3. So this becomes 3 over 4. And then, yeah, it's some value. Let's not waste time on calculating it. And tan 67 and 1/2. So if we double it, we will have 135. But 135 is 180 minus 45. So we should do that when we plug it in. Okay, so that also seems quite simple. Something we could expect in the modern exam as well. Part 2. Prove that sine half of a minus cos half of a is plus minus root. This is not too different from current state exams. I feel that both problem 9 and problem 7 will take a lot of time, so I don't want to include them into this video. But anyway, guys, if this seemed hard to you, remember that there is an advanced level paper available as well. So you will find a link to this paper in the description. Have a look at it. Have a look at the advanced version. And I can personally say that this problem does seem a bit harder than traditional C1, C2, C3, and C4 papers. Especially the geometry questions, because they're definitely non-standard. They do not use out-of-the-book methods there. So I'm really surprised by how difficult exams were back then. Anyway, I hope you enjoy it. If you support this video, I will try and make the advanced level review as well. Otherwise, you can help me get the real background for my next video. So thank you for watching. Like, subscribe, hit the bell. You know the drill. See you next time.